In these slides, we will start discussing how to evaluate recommendations. We will focus here on system accuracy. So when we talk about system accuracy, there are three aspects that we might refer to. First is rating prediction accuracy. This measures how close the predicted ratings to the actual ratings are. For example, if the system predicts a movie rating with 4.3 while my actual rating is 4, rating prediction accuracy considers the difference between 4.3 and 4. Second is classification accuracy. This answers the question if the recommendation is relevant, that is of interest to me. For example, a system has good classification accuracy if it makes 5 recommendations, among which 4 are interesting. Third is ranking accuracy. Here we treat the output of the system as a ranked list, and the goal is to measure if this list contains relevant items. The difference with classification accuracy is that ranking matters, meaning that it's better if we get a relevant item at the top of the list. For example, a recommender has good ranking accuracy if in a ranking of 5 items, the first 3 are interesting. We start with rating prediction accuracy and talk about MAE and RMSE. One thing to remember is that measuring the rating prediction accuracy only makes sense in the case of explicit feedback, that is, when we actually have ratings. So, we want to measure how accurate the predicted ratings are. To do this, we need 2 basic ingredients. First, a way to measure the error between predicted and actual rating, and we have done in the past for collaborative filtering. Typically we compute the squared error, but the absolute error or some relative error could be used. The second ingredient is a way to aggregate individual errors. Usually we take the mean. There are different ways to define these 2 ingredients, resulting in different accuracy metrics. There are, however, 2 important metrics. If we use squared errors and aggregate them using the mean, we get a metric called the mean squared error, or MSE. If we compute the mean of absolute errors, we compute a metric called MAE. Let's get more specific. The prediction error is given by the difference of the predicted from the actual rating. The mean absolute error, or MAE, is the mean over all known ratings. So it looks like this. The root mean squared error, or RMSE, is the square root of the mean squared error over all known ratings. Let's see an example with 10 ratings. The user ID and item ID are shown as the second and third columns. The next 2 columns present the known rating and the predicted rating. The last 2 columns contain the absolute and squared error respectively. It is interesting to see the effects of using the squared error instead of the absolute error. What we see is that when the absolute error is big, like in ratings 1 and 4, the square error has a bigger value, penalizing big errors. In contrast, when the absolute error is small, say 0.1, the squared error is even smaller, 0.01, meaning that it tolerates small errors. This behavior of squared error is what we want most of the times, so that is why RMSE is typically used. And RMSE was actually the metric used to optimize for during the Netflix price competition. A final note about RMSE is that matrix factorization directly optimizes for it. Remember that the cost function contains the squared prediction error. Next up is classification accuracy, where we will talk about precision and recall. Here we will treat a recommender as classifying items for its user. An item is either relevant or non-relevant. In the case of implicit feedback, relevant simply means the item is clicked, purchased, viewed, etc. In the case of explicit feedback, relevant means a high rating, like having at least 4 out of 5 stars, and as shown in the table here. The recommender predicts the class of items for a target user. In explicit feedback, the recommender predicts the rating, so if the prediction is above 4, the predicted class is relevant. In implicit feedback, the recommender predicts the probability of being clicked. There is a probability threshold, say 0.8, so that if an item has higher click probability, its predicted class is relevant. In the following, we assume the case of explicit feedback. So in our example, suppose that the predicted classes are as shown in the last column. We say that an item is actually relevant or not based on the observed feedback. We say that an item is predicted relevant or not based on the recommender system's outputs. Combining these two classes, we have 4 cases for the classification of an item based on its actual status. These 4 cases are shown in the table. True positive is when the item is relevant and the recommender is correct, which means that it correctly classifies the item as relevant. True negative is when the item is non-relevant and the recommender is correct. False positive is when the item is non-relevant and the recommender is wrong, predicting it as relevant. False negative is when the item is relevant and the recommender is wrong, predicting it as non-relevant. Let's continue with our example. So we see the table with the actual and predicted classes and the categorization into true positive, false positive, true negative, and false negative. On the right side, we see a picture demonstrating the concepts we introduced. Each item is a small numbered circle. The big circle in the middle contains all items that are predicted relevant, or equivalently, those that are recommended. The box on the left part contains all actually relevant items. So, in the green intersection of the box and the circle, we have the true positives. The brown part, the difference of the circle from the box, are the false negatives, the items the recommender fails to recognize as relevant. The items in the yellow part of the circle are false positives, while the gray part of the space are the true negatives. We are now ready to define the 2 classification metrics we are interested in. Precision is the proportion of actually relevant items among the recommendations. It is the ratio of true positives over true positives and false positives. Ideally, we want the system to have high precision, meaning that it should only recommend relevant items. Recall is the proportion of actually relevant items among all relevant items. It is the ratio of true positives over false negatives and true positives. Ideally, we want the system to have higher recall, meaning that it should recommend all relevant items. A quick question: what is the range of precision and recall? Well, they lie in the 0 to 1 interval. Convince yourselves that this is the case. The last type of system accuracy is ranking accuracy. Here we'll be talking about precision and recall at specific ranks, talk about average precision, and normalized discounted cumulative gain. It is important to understand that ranks are crucial. What we typically get from a recommender is a ranked list of items. So a system is affected if we get to see good recommendations at the top ranks. Why is that? Because users typically scan a list starting from the top, so more attention is given to the top recommendations, often just a few of them. So how can we capture this notion of effectiveness? Well, let's see if RMSE works. Remember that RMSE measures the prediction error of all items. Does decreasing the RMSE result in better ranked lists? Well, the answer is it probably is. And why? Because if we have similar and small errors for all items, we can safely rank them based on the predicted rating. But more generally, this might not hold, meaning that we can decrease RMSE and get worse ranked lists of recommendations. For example, we might have small errors where we don't really care for items with low ratings. These items will not appear in the top position in the ranked list. So, if we care about the top recommendations being good, we should consider other measures. First, we need to discuss what information we need in order to measure ranking accuracy. There are two components. First is the ranked list of recommended items. Here, we do not care about the actual scores, predicted ratings for explicit feedback, or relevance probability for implicit feedback. All we care is how items rank, how they are sorted based on predicted rating or relevance probability. And the second component is the ground truth, a set of items we know are relevant. Sometimes we might have relevance scores for these items, for example their actual ratings. Sometimes we don't have this information. Okay, so the idea is to adapt the measures of precision and recall for the case of ranked lists. Remember that these metrics were defined for a set of recommendations, not a ranked list. The simplest thing we can try is to consider all recommendations. That is, treat the ranked list as a set. In that case, the relative order between items is irrelevant. And this is something that we don't want. So we can make a small change. We consider only a few of the top ranking recommendations. We take the first K recommendations and essentially cut off the list at position K. The actual value of K is application or domain specific. Sometimes we may care only just for the top 1 recommendation, sometimes for the top 3 or the top 10. So given a value of K, we cut off the ranked list and compute precision and recall at that part of the list. When we do that, we call these measures precision and recall at rank k, and we denote them as P at k and R at k respectively. We can apply this cutoff idea for all possible values of k. That is, we look at the first position of the ranked list, then at the first two positions, and so on. The table shown here computes precision and recall at k ranging from 1 up to 10. We assume there are 5 relevant items. For each rank, there is a precision at k and a recall at k value. For example, at rank 1, we have a relevant item. So, precision at 1 is perfect. It takes the value of 1. Recall at 1 is 1/5, as we have recommended 1 among the 5 relevant items. We can use these two values per rank to draw points in the precision recall plane. We join consecutive points with a line, and the result is the precision recall curve we see in the feature. So, the point at the top left corner is for rank 1, where we have precision 1 and recall 0.2. The rightmost point is for rank 10, where we have recommended all relevant items, so recall is 1. Precision is 0.5, as only half of the recommendations are relevant. There are a few questions you may want to consider yourself to make sure you understand how precision recall curves work. When does the curve go down? When does it go right? Can it go right and down? And what does the best possible curve look like? There is a single metric that summarizes precision and recall scores for all ranks. It's called average precision, or AP. AP is the average of precision scores only at the ranks when a new relevant item appears. That is when the recall increases. Or if you look at the previous precision recall curve at its peaks. So, average precision is not the average of all precision scores. If we look at this table, we do not take the average of the precision at k column. Instead, we look at the bold lines where recall increases and take their average. There are 5 such ranks, and the average precision is 0.717. Ranks are important, but so is relevance scores when available. Remember that these scores capture how relevant the item is for the user, and in the case of explicit feedback, it's the user's rating. For implicit feedback, we probably cannot distinguish between relevance scores. Okay, so precision and recall does not consider relevance scores. They only look at how many relevant items are there and not at how much relevant these items are. Let's see an example where precision of 5 is 0.4, meaning that 2 relevant items appear in the top 5. The same precision value happens when both items are highly interesting, for example, have a high rating. And the same precision value occurs when both items are only slightly interesting, for example, have a relatively low rating. So, precision and recall cannot differentiate between these two scenarios. And that is the problem NDCG, or Normalized Discounted Cumulative Gain, tries to solve. It cares both about ranks and relevance scores. Before we see how it works, let's build some intuition. Consider two recommendation lists R1 and R2. First, assume that the same rank is occupied by different items. For example, at rank 1, R1 puts an item with actual rating or relevance score 5, while R2 an item with rating 4. So which one does a better job? Well, R1 utilizes this rank better, placing a more relevant item here. How much better? Well, this depends on the relative importance of the two items. Specifically, assume that the same item is at different ranks in the two lists. For example, R1 puts it at rank 1, while R2 at rank 2. So the contribution of the item is higher in R1 compared to R2. But how much higher? This depends on how much more visible is rank 1 to rank 2. Several studies have shown that the relative importance depends on the logarithm of their ranks. So we might get something like 1.59 times more important. Okay, so let's see how NDCG works. We have a ranked list where item ij denotes the item at rank j in the list. Then let ruij denote the relevance or rating of the item to the target user. The discounted relevance of the item due to its rank in the list is given by this formula. Essentially, the rating is multiplied with the logarithmic discounts, whose plot is shown here. For the first position, the discount is 1. Then, at each subsequent rank, it drops slowly. The discounted cumulative gain at k, or DCG at k, is the sum of discounted. The DCG value depends on the position of the rated items and their ratings. The best possible DCG is called the ideal DCG. This is the ideal ranking that contains all relevant items at the top of a list, sorted decreasingly by relevance. Then, the normalized DCG at k, or NDCG at k, is the DCG at k divided by the ideal DCG at k. Let's see an example. The first column shows the ranks from 1 to 10. The given recommendation list is shown in the next columns. Here, there are 5 relevant items placed at ranks 1, 3, 6, and 10. The second column shows the relevance score of each relevant item. The third discounts the relevant by their rank. The column DCG at k sums up the discounted relevance up to a rank. So the first recommended item is relevant, with a rating of 5, which is discounted by 1 to give the NDCG at 1 equal at 5. The second recommended item is not relevant, so DCG at 2 is also 5. The third recommended item is relevant, with a score of 4. This third ranking is discounted by 1/2, so the discounted relevance is 2. As a result, DCG at 3 becomes 5 plus 2 equals 7. The next 3 columns in the table correspond to the ideal rating. As shown in the next column, The 5 relevant items are placed at the first 5 positions and are sorted by the relevance score. Therefore, the 2 items with rating 5 are the first 2 positions, followed by the 2 items with ratings 4, and finally, an item with rating 3 occupies the 5th position. The discounted relevance and cumulative gain are shown in the next 2 columns. Note here that after rank 5, there is no relevant item, so the IDCG at K remains at its highest value, 13.04. And the last column simply divides DCD with IDCG to get NDCG. So we have now seen various accuracy measures. Let us now discuss how to apply them to evaluate a recommender. We have seen that recommenders rely on some historical feedback data in order to make recommendations. For example, we saw that memory-based collaborative filtering compute user-to-user or item-to-item similarities based on this historical data. Model-based collaborative filtering builds a model out of this data. So we call this data the trained dataset. In general, recommenders try to make their best out of the trained dataset. For example, build a model that accurately predicts these known ratings. For the evaluation to be meaningful, we should not measure accuracy on this trained dataset. The reason is that the performance we see might not actually be the performance we get in unseen ratings, as the recommender might overfit the trained dataset. So, we should evaluate on a distinct test dataset that is hidden from the recommender. However, the train and test dataset should have similar distributions. So, if we have collected some historical feedback data, we must split them into a train and a test dataset. The train dataset will be known to the recommender so that it can build its model, while the test dataset will be used to evaluate the recommender. The question is how to split the dataset. Well, in some cases, the split might be given. For example, we leave for the test dataset certain hard cases that we care for. However, in most cases, you should perform the split. This means that you decide on a split ratio, something like 80% train, 20% test, and randomly partition the historical dataset. The previous discussion about train-test split applies in general to machine learning algorithms. When evaluating recommenders, we should pay some additional attention. A recommender is doing well when it makes good recommendations for all users. This means we want to make sure we get a measure of performance for each user. So the test dataset should contain ratings from all users. We say that the split must be user-aware and not just any random split. If we want an 80% 20% split, then we should look at the historical feedback of each user and select 80% to place in the trained dataset and the rest to the test dataset. Once we have a trained test split, we can use the test dataset for the evaluation. Next thing on the agenda is how to report the evaluation metrics. For rating prediction accuracy, we should compute the metric like MAE or RMSE over all ratings in the test dataset. For classification and ranking accuracy, we compute the metric for each user individually. Then we compute the mean metric across all users. This is the value we report. For example, if we care for NDCG at k, we should compute NDCG at k for each user separately and then report the mean across all users. As a side note, when we compute the average precision across all users, the value we report is called the mean average precision. And this is not the case for other metrics. That is, although we compute the mean NDCG across users, people just refer to it simply as NDCG. One last thing to discuss about evaluation concerns the model-based approaches, which typically have a number of hyperparameters, variables that control the training process but are not learned during training. For example, in matrix factorization, the number of latent features k is such a hyperparameter. The question is how to set the values of the hyperparameters for the training. Well, the idea is to try out multiple values and select those that work best. The only caveat is that selection should be done based on the performance of a discrete subset of the historical data. For that reason, we reserve a small part of the historical data called the dev or validation dataset. So now we have three partitions: train, dev, and test. And typically their size ratio is something like 80%, 10%, and 10%. So to recap, the evaluation protocol is the following. We define a series of hyperparameter values that we want to test out. Then we train a separate instance of the recommender on the trained subset for each combination of hyperparameter values. Then we use the dev subset to do internal testing and decide which combination of hyperparameter values to keep. After fixing them, we go ahead and measure the performance on the test dataset. So, how to produce a dev dataset? The standard approach is to leave out the test dataset and split the other part of the historical data into the train and dev subsets. And the simplest way is via holdout. Like we did for the train test split, we randomly split the non-test data in a user-aware manner. The most typical case, however, is to perform k-fold cross-validation. So, k-fold cross-validation means that we create k different folds or partitions of the trained dev data. The evaluation metrics will be the average across these k folds. So first we divide the data into k equal parts in a user-aware manner, and for each fold we pick one part to be the dev dataset and the other k-1 parts to act as the trained dataset. The figure shows an example with k equals 4 folds. As said before, to decide on a hyperparameter combination, we compute the evaluation metric of interest of each dev dataset in each fold. We then compute the mean over the k folds.